Hey there, in this video I want to talk about aliasing and the Nyquist frequency. So we've already seen, looking at the discrete Fourier transform, that we have this kind of mirror imaging, that half the coefficients are complex conjugates of the other half. So let's start with a sine wave. And we're going to sample it. So we're going to start with a function that describes what the sine wave looks like everywhere. F will be frequency, t will be time. And we're going to return sine times 2 pi times the frequency times time. Okay, and this 2 pi frequency here, this is the difference between angular frequency and cyclical frequency. And what we're usually going to be working with here is frequency like in hertz. So do be careful. There is a 2 pi difference between omegas and f's, and we are using f's here. Anyway, so this function would give us a perfectly smooth sine wave if we evaluated it everywhere. But let's evaluate it at 20 points. So we're going to say here that our starting f will be 1. Okay, this is like the frequency of our sine wave, because our function can take any frequency. We'll just make it 1 for simplicity. We'll make our dt 0.2, so this is seconds per dot. Let's put some comments here. Okay, so this is our frequency with units of hertz. And this is our time spacing, so this is like, called seconds per dot, and I'll draw dots on the graph here. We can calculate this Nyquist frequency just using the equation above, so that would be 2 times dt. We can calculate our delta f, I'll call it df here, as 1 divided by n times dt. Okay, so it's like our resolution. And now let's make some graphs. Okay, so let's start with a sampled value for time. So that will be relatively low resolution array. We'll go 0 to n times dt in steps of dt. Okay, so that'll have n values in it. And then we'll also make a smooth version of time. So we'll do the same kind of thing. We'll go 0 to n times dt, but we're going to take tinier steps. So let's take steps that are 100 times smaller, and so making our graph 100 times smoother. We'll do the same kind of thing with y. So y sampled will be a low resolution version of y that we get by passing in our frequency of 1 hertz and our sampled time array. And then, as you might guess, we're going to also do y smooth, which will be y, giving it our frequency, and t smooth. Okay, so this should give us some arrays to look at. Best way to visualize them is to plot them. I'll plot t smooth and y smooth. And then on top of that, we'll do the sampled. T sampled and y sampled. I think a solid line makes sense for the smooth array, but for the sampled one, let's go with discrete dots, because there's a lot more spacing in between them. Okay, and then I don't know if we really have to do this, but we'll just say that put our x label in here. Just remind us that this is units of seconds, and we'll compare that to the Fourier transform stuff, which will have units of hertz. Okay, and now what's it mad about? T sample is not defined. Why? Oh, because I called it sampled, not sample. Okay, and so, I mean, these graphs line up with each other. Nothing too surprising there. Now let's look at what happens when we start taking some Fourier transforms. So we'll use SciPy here in FFTPack, specifically the FFT function out of it, to do the Fourier transform of our sampled array. Okay, and so that's going to be the Fourier transform. We want to plot that as a function of frequency. And so to calculate the frequency, we make an A range. Now, like, what kind of range should we have here? We would clearly start at 0, but how far do we go? Well, we want to go to 1 on dt here. So like dt is our time spacing, or maybe a better way to put this is we're going to twice the Nyquist frequency. Maybe we should just put that in here. That way. Did I calculate F9? Yeah, okay. So it's the exact same thing. 1 on dt, or 2 times the Nyquist frequency. And I'm going to double the Nyquist frequency so we can see this mirroring effect called aliasing. And then we're going to take steps of size df, which I've already calculated up here. So like this is me calculating what is my frequency spacing based on what I put in the first place. So this basically gets the units right. Notice the sample units are not one apart, but they have this different value apart. So now we can plot frequency and our Fourier transform. Since it's complex, we're going to plot the absolute value of C so that we aren't effectively hiding the imaginary part, which in general is non-zero. We're going to do this as lines with dots on them, just so we can sort of see the spacing. And let's draw a vertical line, an XV line, and we're going to put it right on the Nyquist frequency. And we're going to make it black. Okay, and so like we did before, let's put some units on here. So our X label here is going to be frequency in hertz. Okay, so here's our frequency in hertz, and you can see we have a peak at 1 hertz, which makes a lot of sense. We set this up originally way up here with f equals 1. Okay, so we said, hey, I want a peak at 1 hertz. But you'll notice here at the Nyquist frequency, we have like a plane of symmetry, and we also get a peak at 4 hertz. There's no 4 hertz in this sine wave. What's going on there? Okay, so let's look at what is happening here. So first of all, let's make a new version of smooth here, y smooth. That's going to be our function y at 4 hertz. And you'll just see like what does that look like? We'll do that as a function of t smooth, which is unchanged from before. So we're going to plot t smooth and y smooth, and we're going to plot t sampled and y sampled. These are unchanged from before. We want those to be dots. And let's show them. I'll leave off the X label for this one. And we can see, yeah, 4 hertz really doesn't line up at all. Now, the really crazy, mind-blowing part is if you want this to line up, you have to make it negative 4 hertz. And then it lines up. Okay, now, what is happening here? So what is happening is, if we look at like this higher frequency sine wave, it manages to hit all of our points. We have this phase shift in here, but other than that, it manages to hit all of our points. And that's because there's more than one way to connect these dots. It turns out 1 hertz and 4 hertz are going to connect the dots. And why those values? It has to do with this Nyquist frequency. This is sort of our symmetry point. Now we have that business with complex conjugates on either side, and that is analogous here to phase shifting our sine waves. So that's why it's a negative 4. That's also kind of a variation on, if you remember when we did the continuous Fourier transform, we had negative coefficients and positive ones, like negative values of k and positive values of k. And when we do the discrete transform, effectively all the negative values get squished over here on the right. It's not quite right to call them negative anymore, but they are analogous to those old negative coefficients, and that's sort of like why it works with a negative sign here. Okay, now, beyond that weirdness, the takeaway here is we can get some really weird frequency results out of our Fourier transform if we aren't sampling very well. If our Nyquist frequency isn't high enough, then we get some strange stuff. Okay, so we're going to now build up another example. This one will be an animation to show us what kind of weird frequencies we can get coming out of here. So if I'm going to make an animation, I need some more libraries imported. All right, these are the nice duo here. Oh man, it's mad at me. Okay, that's our duo here for making animations. And now we want to quickly try to build up an animation here. So since I'm going to do this quickly, I'm going to do kind of the brute force form of animating where I just clear the figure every frame instead of updating different objects. It's just quicker code to write, even if it'll take a little longer to run. But hey, I can just cut that part out of the video, so it'll be fine. What I want to do here is make a function that has 2 frequencies in it, f1 and f2, and I want those frequencies to be 20 and 30 hertz. And so let's write that function. We'll do it y is a function of t, and we're going to return, we'll just make up some kind of amplitude here. So we'll go 3 times sine of 2 pi times f1 times t. So that'll give us that first frequency, and then we'll do a subtraction. An addition would be pretty similar. We'll do a cosine. Doesn't really matter if these are sines or cosines. 2 times np dot pi times f2 times t. Okay, and so the frequency content of this function should be 10 hertz and 30 hertz. So let's see what we actually get. So I'm going to recreate t-smooth here. I want it to have a different range. So I'm going to have it go from 0 to 10 in steps of 0.001. Okay, so that should be actually a disgusting number of steps here in smooth. And then for y smooth, that will be y of t smooth. You know, that might even actually be too much. Now that I think of it, that's like 10,000 steps. That'll be 1,000 steps. That should be enough. We'll boost it up again if it's not pretty for whatever reason. Okay, so those are our smooth values. We'll just evaluate a function like everywhere. And now to make an animation, I have to make a figure. So that'll be a plot.figure. We'll make it kind of big. I don't know, I feel like the more complicated the animation, the bigger the figure should be. It just like feels better. So we'll go with an 8x4. I'm going to make a progress bar just so I know if this code is actually doing anything. It's not really necessary for it to work. I'm going to do 100 steps in my progress bar. I'm also going to have 100 frames in my animation. So those will match up nicely. And then we will display the progress bar. Okay, so now we'll create an animate function that takes frame as an argument. And what it's going to do, first of all, is it's going to update the progress bar. Right, most important thing. Progress. And we'll make that equal to frame plus 1, remembering that frame starts at 0, and we want the first tick on our progress bar to be 1. Okay, and then we want to figure out, or what we want our animation to do here is change what dt is. Basically change the sampling of this sine function. And as we change the sampling in Fourier transform, we're going to see that our answer will actually start to change when our sampling gets too broad, causing an effect from this aliasing. So we're going to build dt based on the frame. We're going to start with 0.01 seconds, and then we're going to make dt bigger, which is actually worse for what we're trying to do. And we'll just make it bigger by frame on 1,000. So as frame goes from 0 to 100, we'll go from 0.01 up to, I guess that would be 0.02. Should work. Again, we can play around with any of these values if it's not quite what we want. Okay, now we're going to do some sampled here, kind of like before. So we'll A range here, we'll go 0 to 10, and we'll take steps of t, and then y sampled will be based on calling that function y. So we'll call y here at t sampled. And I don't think I need to vectorize this because it's written with arrays already, so I think that'll be fine. Let's calculate some special values. The Nyquist frequency here, just using its definition, is 1 on 2 times dt. I wrote dx in the generic equation at the very beginning, but here t makes more sense. Let's see, what else? How many points do I have? Well, that's going to be whatever the length of t sampled is. And the length is going to be changing as I change my delta t. So, you know, it's convenient just to have a variable for it. Okay, now the frequencies. So the frequencies, I think safest way to do them is build them with a linspace. I'm going to go from 0 to 2 times the Nyquist frequency like we did above. So we see that mirror imaging, and we know there's going to be n of them. It's important that these arrays have the same size consistently throughout, otherwise we're going to get errors when we try to plot them. So having n here just guarantees that the arrays will definitely be the same size. And then, so we want to plot FFT as a function of frequency, and so the FFT comes from FFTPack, where we're going to throw in y sampled. Okay, so I think this is all the calculating we need to do. We've got, well, we have the smooth ones pre-calculated, and then we're going to do sampling with different DTs. I haven't used the Nyquist frequency other than setting a limit here, but we'll use it when we graph. Okay, so I'm just going to do like the brute force animating. I'm just going to completely blow away the whole figure every frame. So it's easier code to write on the fly here. And so what I'm picturing here is I'm going to do 2 rows. The top row is going to show me the Fourier transform, and the bottom row is going to show me the function, both smooth and sampled. So on the top row here, so this would be 2 rows, 1 column, graph number 1. I'm going to start by giving it a title. And that title is just going to be some text to let me see what these variables are doing. So I want to keep track of what is the current dt. And so we'll make that equal to dt, and we'll do 3 decimal places. And I want to keep track of what the Nyquist frequency is. So we'll make equal to f9, and we'll do that to, let me think about this. The Nyquist frequency should be fairly large. I mean, we should be like 50 hertz or something like that. So we'll make it 0.1f. That should be enough. Okay, so now the top graph is going to be the Fourier transform one. So I want to plot frequency and the absolute value of the Fourier transform, keeping in mind that this is generically complex. And then let's do it as, we'll do a dot dash for that, just so we can see where the discrete points are. I think it would be nice to draw a vertical line like we did in the previous graph at the location of the Nyquist frequency. We'll make it black. Good idea to set the x limits here instead of having it guess for us. So we'll go to twice the Nyquist frequency, so to match our range. I mean, I think it would pretty much auto scale the way we want, but you know, just to be sure. Okay, let's make another subplot. This one will be 2 rows, 1 column, graph number 2. I don't think we need a title for this one. We're going to do smooth and sample. So we'll start with the smooth underneath. So T smooth and Y smooth. And let's make them like a nice light color like gray. I can't just call this G because that would be green. As far as I know, I have to type out the word gray. Okay, and then we're going to do the sampled. Sampled and Y sampled. Let's go with dot dash lines. I think would be good. Make them red. Dot dash here, I mean, this is going to give us dots and then connect the dots. Not quite the same as, I guess I really shouldn't call it dot dash, but well, you'll see what it looks like. Okay, and then plot.xlim 0 to 1. I think I will put the labels on here. So this one's time in seconds, and the other one is a frequency in hertz. Just so it's easy to remember what we have once we have it beautiful and we're looking at it. Okay, and the rest should be boilerplate code. So we'll call it an anim. It'll be built from a func animation. Take fig, we'll take animate, we'll set the frames to 100. We'll do an interval of, let's do 100. That might be a little too fast, but well, we can always pause it. Okay, and then the video will be an anim to something like HTML5 video. Doesn't want to autocomplete for me. I'm pretty sure it's HTML5 underscore video. It'll yell at me if that's not the right way to spell it. And HTML is going to be from the display module. So we'll take that video and turn it into HTML. And then we want to display it. Okay, well, we made a figure, right? So we should close it so we don't end up drawing a duplicate. And I have a progress bar too, so I want to clear that out. Always nice to clean up. Okay, so we'll do a display dot clear output. And I think it's weight. Yep, weight equals true. Okay, so this is just this line here is just to erase the progress bar. It's important that it comes before we display the final animation, otherwise we'll erase the animation just as it finishes, and that's so sad. Okay, now there's like a 0% chance this is going to run without any errors, so let's just start that debugging. Oh wow, it's actually running. And here we go. Let's make that full screen. Okay, so we can see some crazy stuff's going on. So down here, this is our sampling. We're changing our delta t, so we started sampling at pretty high resolution, matching the function pretty well, and as we go into lower resolution, it's not matching as well. Okay, so let's start here. This has got pretty good sampling, so you can see our sampled version looks a lot like the underlying array. So it's looking pretty nice for us. And here's our frequency graph, and I've got a peak at 10 and 30. Exactly what I'd expect. Now, after we pass the Nyquist frequency in kind of garbage land, we also have peaks at 70 and 90. And these are mirror images of the other. So you say, okay, no problem, we'll just ignore that stuff. I should be able to use the arrow keys here. Now let's see what happens as our sampling goes down, our Nyquist frequency goes up. And you can see it's getting really kind of close to the 30. Really close, really close. Now I've passed the 30. So what's happened here is I can only distinguish frequencies up to 25 hertz, but I contain a 30 hertz in my signal. So what has happened here, if we look at how our dots are connecting, we kind of like skipped some of our peaks. And we've gotten this case where the 10 shows up just fine along with its mirror image, but our 30 is on the wrong side of the Nyquist frequency. So instead we see its mirror image over here. And so it looks like there's a 20 hertz signal, but it's really just a mirror image 30 hertz signal. And if you didn't know what the underlying gray curve was, you wouldn't know this happened. You would have sampled poorly. And you'd have, the effect here is called aliasing. So anyway, we keep turning the spacing up. We can hit the case where 10 and 30 are mirror imaged around the Nyquist frequency, and it looks like now this is just a single sine wave based on how we've sampled it. So we've completely lost one of our frequency components. That's also terrible. Okay, now we keep going, and you can see as we make our sampling huge here, we run into danger of losing even the 10 hertz signal. Send that to the other, well, I guess you could have everything at the Nyquist frequency, but here's something like this, where it looks like we have components at like 2 hertz and 6 hertz, but really they were 10 and 30, which got wrapped around a few times. So anyway, the message here is if you don't sample your data with a high enough resolution, you can get really basically nonsensical results from doing your Fourier transform here. You know, and that has to do with how it gets sampled down here. I mean, like if you connect these dots, like if these red dots are all that exist, it really kind of looks like there's just this sort of real low frequency sine wave, you know, at 2 hertz, and maybe a higher frequency component at 6 hertz. I mean, that's what it looks like. So again, you just have to be careful about what you're doing.